Hi, my name is Aishani and I'll be testing linearity. To test linearity, I created a residual versus fitted plot, and the plot shows a clear curved line indicated by the blue. This shows that the model is nonlinear as residuals are not randomly distributed around zero. A transformation to the model may improve the fit. We also created a partial regression plot, and for each of the variables, percent unemployed showed a weak but roughly linear trend. Percent population under poverty displays notable curvature and shows a nonlinear relationship. Lame-ass percent police on patrol shows a relationship that appears mostly flat and shows no clear nonlinearity but a weak predictor. Poverty tier low and mid have points that appear in clusters and no linearity issues. To conclude, both plots show nonlinearity, and these can be fixed by adding a polynomial term for percent population under poverty. The improved model shows that nonlinearity is corrected by the fix, as indicated by the residuals versus fitted model, where the blue line is roughly flat and close to zero. The new model would be total crimes per population equals beta 0 plus beta 1 times percent unemployed plus beta 2 times percent population under poverty plus beta 3 times percent population under poverty squared plus beta 4 times lame-ass percent police on patrol plus beta 5 times poverty tier plus beta 6 times poverty tier mid plus the random error.
Hi, I'm Ishaan Handa. I'll be covering the constant variance assumption, also known as homoscedasticity. This assumption requires that the spread of our errors stays consistent across all predicted values. If it doesn't, our standard error becomes biased, and we can't trust our p-values or t-statistics. To check this visually, I'm looking at the residuals versus fitted plot. What we want to see is a random cloud of points with roughly equal spread from left to right. What we actually see is the opposite. On the left side, where fitted values are around 4,000 to 6,000, the residuals are clustered tightly together. As we move right, toward the fitted values of 12,000 and beyond, the spread fans out significantly. That asymmetry is a clear visual indicator that variance is not constant across our predictions. The scale location plot makes this even clearer. The y-axis here is the square root of the absolute standardized residuals, which is essentially a measure of how large our errors are at each fitted value. If variance were constant, that red smoother line should be approximately flat. Instead, it trends upward from left to right, confirming that errors are getting systematically larger as our predicted crime rates increase. The problem is most pronounced in the 8,000 to 12,000 fitted value range, which corresponds to communities with mid to high predicted crime rates. To back this up formally, I ran the Brodie test, which tests whether the variance of residuals can be explained by our predictors. Our BP statistic came out to 28.30 with a p-value of 0.000032. That is far below our significance level of 0.05, so we reject the null hypothesis of constant variance. This isn't just a visual impression. Heteroscedasticity is statistically confirmed, and it's consistent with what both plots showed us. So what did this mean for our model? When OLS assumes constant variance, but that assumption is violated, the standard errors it computes are biased. Some will be too small, some too large. That means our t-statistic and p-values for all coefficients are off, including the ones that look significant, like percent population under poverty and poverty tier low. We can't fully trust those interference results as is. The most practical fix is HD robust standard errors using the sandwich package in R. This adjusts the standard errors to account for heteroscedasticity without changing the coefficient estimates themselves. Alternatively, the team could apply a log or square root transformation to the response variable to stabilize variance, or use weighted least squares if we can model how the variance changes. Overall, this is a serious violation that the model should address before drawing strong conclusions from inference.
So let's look at the normality of errors. First one is histogram, and from the graph we can see that the residuals are centered around 0, mostly falling in between -5,000 and 5,000. There is a slight right skew, but it is basically symmetrical. So practically, it is close to normal since there's no severe skew or outliers. And the next one is QQ plot. The general shape is a straight diagonal line. Although there are some extreme points there are 3 points on the left bottom and 2 points on the right top, but it is visually close to normal. And then next we run the Shapiro test. The output says that the p-value is negative 0.0025, so statistically at 0.05 significance level we reject the normality. However, if we look at the W value, it is 0.98 here, which is very close to 1. So, in conclusion, while the Shapiro test returns a small p-value that rejects normality, the histogram and QQ plot suggest otherwise. Both show residuals are approximately normally distributed, and also the W statistic of 0.98 from Shapiro test is very close to 1, so that confirms that the practical departure from normality is basically negligible. So overall, the residuals can be considered approximately normal. Given that the normality assumption is satisfied and the sample size is 300, t-test and the f-test are reliable for inference. The few extreme observations in the QQ plot may affect standard errors, which could slightly widen the confidence intervals, but this is very unlikely to change any significance conclusion.
Hello, my name is Neeil Gupta. So I ran 3 diagnostics to catch problematic observation. Cook's distance flagged 25 points, leverage flagged to 18, but only 3 actually crossed the standardized residual cutoff of 3, which were observations 6, 75, and 172. The observation 6 is the worst, where there's high leverage and it crosses the -3 line, so it's bad on both fronts. Observation 61 has a leverage of 0.177, which is large, but a normal residual, so it's just pulling the fit in the predictor space. Observation 172 is the opposite, where it has a massive residual but low leverage, so it's just a community with a weirdly high crime rate for its profile. And observation 191 has high leverage, but lands almost exactly on the fitted line, so it's not doing too much. But removing those 25 points barely moves percent of population under poverty, only plus 6.6, so the poverty crime slope is pretty solid. But poverty tier low shifts by 471 and poverty tier mid by 337, which means these points were dragging the tier coefficients down and making tier differences look bigger than they actually are. R squared also jumped from 0.435 to 0.505, so continuous predictors are fine, but tier coefficients need to be read more carefully. For the interaction, I tested whether poverty rate's effect on crime actually changes by poverty tier. The partial f-test came back at p equals 0.070, which just misses the 0.05, and R squared only gains 0.01, so overall the interaction is marginal. But inside the model, one term does hit significance, which is percent population under poverty times poverty tier low, which is p equals 0.026. The slopes are 381 for high tier, 346 for mid, and 281 for low. So poverty hits crime hardest in high tier states and flattens out in low tier states. And you can see it clearly in the plots with the lines fanning apart as poverty increases. The raw scatter confirms this pattern, but the confidence bands overlaps a lot, especially in the middle range where most data lives. And this is consistent with marginal f-test, and it shows that the interaction is real, but not overwhelming.
All right, this is Brodie, and I'm going to be going through multicollinearity in the model. So the first thing we looked at, I think we did this in a previous video, but I made the correlation matrix again, and again found that the poverty rate and unemployment rate have pretty high correlation. The rest of the variables don't really need to worry about. And then looking at the VIFs on the model, poverty and poverty tier have a very high VIF that we will need to fix. In order to look at those things, made some graphs, scatter plots of the variables against each other, and it found that poverty rate versus poverty tier, obviously you can see there's a definite relationship there because each category of poverty tier has a different distribution on poverty rate, which makes sense because obviously they're basically measuring the same thing. One is just categorical and the other is not. But then plotting unemployment rate versus poverty tier or poverty rate didn't really show a definite relationship. So maybe don't need to worry about that as much. And then looking at models of each of those, where I just took out one of the three variables each time, as you can see. Removing either poverty tier or poverty rate made the models a lot better. You can see the coefficients are more realistic, whereas before the coefficients for the poverty tiers and poverty were negative. Removing one of the variables kind of fixes that. And the BIFs are a lot nicer. Whereas taking unemployment out didn't really have any kind of positive effect. So therefore, we can probably say that poverty rate and poverty tier are very collinear, whereas unemployment rate really doesn't have collinearity. And what that means in terms of using the model is we can use it still to predict values. It's still accurate in that way, but to predict the coefficients or to estimate the coefficients or the parameters, probably not a good model to use. So if we wanted to do that, we would have to drop one of those two variables.
So, in conclusion, linearity was violated, but that was fixed by adding a polynomial term for poverty rate. Constant variance is the most serious violation, and the Bruce-Pagan test confirmed heteroscedasticity, which means our standard errors are biased. Normality has a minor statistical violation, but with 302 observations, the central limit theorem covers us, so that one is not really a concern. Multicollinearity is moderate. Poverty rate and poverty tier overlap a lot, which inflates the standard errors, and outliers are present, but the continuous prediction stayed stable, so that is manageable. But can we trust this model? For the most part, yes. The poverty-crime relationship holds up across every single diagnostic we ran, and it is the most reliable finding in this whole analysis. The biggest problem is heteroscedasticity. Our standard errors are biased right now, which means we cannot take the p-values completely at face value without first applying robust standard errors. The poverty tier coefficients also need some caution since they shifted a lot when we removed influential points, and they share a lot of variance with poverty rate. But overall, the model tells us a credible story. We just need to apply robust standard errors before making any firm conclusions off the p-values.